see the use of vectors and see the use of the various vector operations in practice, and allow us to get a handle on that. So we're going to look at applications 2.4 and look at number 1 here. Which is this, to solve the problem of closest approach of 2 lines in 3 dimensions. Okay. Okay, so given 2 lines, L1 and L2 in 3 dimensions in R3, find where they make the closest approach to each other. Maybe they intersect each other. Of course, for 2 lines in 3 dimensions, it's extremely rare to have the lines actually intersecting. We kind of have to design them for that to happen. Most lines in 3 dimensions won't intersect each other. But there will be a location on the lines where the lines come closest to each other. Now, it could be that the 2 lines are exactly parallel. So there's no specific location where the 2 lines are closest to one another. But then again, that's a pretty fluky, pretty unusual situation. 2 lines in 3 dimensions being exactly parallel. Typical solution is you have 1 line here, another line here. They spend a lot of time far apart, but then at some point on the 2 lines, they become the closest distance between them. Okay. So we want to solve that. So we'll give ourselves a little sketch to indicate this. So here's L1, and we'll put L2 coming through here. This is a typical situation. 2 non-parallel, non-intersecting lines in 3 dimensions. From whatever viewpoint we're using, L1 is kind of in front of L2. And there's going to be some point on them. Let's just say it's up here. Point on L1 and a point on L2, and this distance is going to be the shortest distance between the 2 lines. And we want to be able to obtain that. Okay, so how did we say the 2 lines would be given to us? Well, we decided on a vector description of a line. A vector description of a line, well, one of the ways was having a fixed reference point on the line and then a direction vector for the line. So I'll just add some annotations to the diagram. So L1 is given by position vectors R position vectors R1 satisfying. So what does R1 look like? R1 of the R1 vector, and you can think of it as a function of t. So this is going to be vector p, the fixed reference point on L1, plus some scalar multiple of the direction vector p. Okay, when t is equal to 0, you're at this point by yourself. As t goes positive, you go along the line in this direction. As t goes negative, you come backwards along the line L1 in this direction. Similarly, L2 is given by same thing, by position vectors R2 satisfying R2 is going to be Q plus, we use a different letter for the parameter associated to R2, and Q plus S times W. So this is, R1 is what points on the line L1 look like, and R2 is what points on the line L2 look like. So this red vector that we're looking at here, the line joining a point on L1 to point on L2 has the form, well, R1 minus R2. Which is going to be P plus TB minus Q minus SW. So we got an expression that captures that little red joining segment I've done between the two lines. Okay, it relies on these two parameters, T and S. T governs where the point is in L1, S governs where it is on L2. Now we seek the minimum distance of this line. We seek the minimum value of the magnitude of R1 minus R2. Now, if we had the individual coordinates of R1 and R2, we could use the Pythagorean formula for the magnitude of the vector, namely the square root of the sum of the squares of the components. And we could introduce those individual components of R1 and R2 by specifying, by labeling the individual components of P as P1, P2, P3, Q as Q1, Q2, Q3, and so on. But that would multiply the number of symbols I was using and introduce square roots in that. So there's maybe a cleaner description of it, i.e. we seek, and one that will help us a little bit, we seek the minimum value, or we seek to minimize the square of the magnitude. Why should I want to minimize the square of the magnitude? Well, the magnitude is minimized at the same time, at the same location, the same instant that the square of the magnitude is minimized. But this has the square of the magnitude of a vector has a neat description using another vector operation that we know about. Okay, that's the dot product of the vector with itself. Isn't it? R1 minus R2 dot itself, R1 minus R2. Okay. And it's, since I have nice vector expressions, since I have a nice vector expression for R1 minus R2, I can fairly easily get one for R1 minus R2, taking the inner product with itself. Okay, so what we'll do is we'll write R1 minus R2. We'll just package it up a little bit differently. As P minus Q plus plus TV minus SW. Just package it up a bit like that. So then take the inner product with itself. Well, I'm going to get a term which is the inner product of P minus Q with itself. Put P and Q together like that because P and Q are both specified as part of the problem. They're the two fixed reference points. So this quantity here, the magnitude squared of the vector P minus Q, that comes to us easily as part of the set. I'll then get, when I take the inner product of this with itself, I get T magnitude of V squared, sorry, T squared, and then I get a plus S squared magnitude of W squared. So those are taking the inner product of each of these three terms in R1 minus R2 with themselves, but then you'll have all the cross inner products as well, which will all occur with multiplicity 2. So I'll have then plus 2t, and there's p minus q dot product with v. Then I'll have minus 2s p minus q, the dot product with w. So that's p minus q with this, p minus q with that. Then I just need to take this one, which would be minus 2 times s times t times the inner product of v with w. So some of the, when I'm taking the inner product of R1 minus R2 itself, some of the terms I'm writing as inner products, but when you have a vector inner product with itself, I'm choosing to write that as the magnitude of that vector squared. Okay. Now we'll give this a name. Let's call this. We'll choose to call this, just to say just a quicker way of denoting it, delta squared st. So delta is standing for the magnitude of R1 minus R2, and it's squared, and it depends on two variables s and t. So we can link this back to some of the MATLAB stuff we've been doing, because we recognize this now as a function of two variables. Now, in a few lectures' time, we'll be going on to consider how you find stationary points, optimum points, minimums and maximums of functions of two variables. But for now, we'll just take a bit of that theory here to say that the minimum value of this function, which is called delta squared, two variables, the s and t, this is achieved. It's achieved when the two partial derivatives, ds and d delta squared dt, it's when they're both equal to 0. I think I briefly mentioned that in the maths methods lecture, but we'll come on to consider it in detail pretty soon. So the minimum value of this squared magnitude of R1 minus R2, it's going to be located, it's going to happen when both of the partial derivatives are equal to 0. Now, when both of the partial derivatives are equal to 0, this could be a maximum point as well. But I mean, I think it's clear when you glance back to the original diagram in this typical setup, there is no maximum value that this distance between 2 points and the two lines can have. So you can just send the points far down the lines away from each other, and it's clear the distance can be made as large as you want. Unless, yeah, you can make the distance as large as you want. So there is no maximum distance. So the solution to these partial derivatives equal to 0, this is going to correspond to the minimum distance. So this gives us two equations. Two equations here. So first we'll look at d delta ds. So this expression I just had up here a moment ago, I want to differentiate it with respect to s. Okay? So s and t are the variables. Everything else, although it looks quite complicated, all the other parts of that expression, all the vectors, the p, the q, the v, and the w, they're all fixed constant vectors. P and q are the two fixed reference points of the lines. V and w are the two direction vectors of the lines. They're all fixed quantities. So all these inner products will be fixed quantities. So for the purpose of differentiation, they're all just constants, multiplying the terms in s and t. So the first time you see an s is here in the s squared magnitude of w squared. So that's going to give you a 2s magnitude of w squared when you differentiate it. There's no s here. And you see there was no s in these two, so they have a derivative at 0. There is a s here, so I get a minus 2 times the inner product of P minus Q of W. And then there is an S there, so that's going to give me a minus 2T inner product of V with W. And this is all equal to 0. Okay, so we're doing partial differentiation. This expression delta squared. We do the same thing now, but with the variable t. So d delta dt. You go along looking for the t's. Well, there's no t here, so it has a derivative of 0. There's a t squared magnitude of v squared there, so that gives us a 2t magnitude of v squared. So it's kind of mirroring what we had before with s. There's no t there in s squared. There is a t here. It's going to be plus 2 p minus q inner product with v. There's no t there. There is a t there, so it's going to give me minus 2s inner product of v with w. So, so the minimum value, the distance between the two lines, is going to be minimized at the solution of these two equations. And these two equations, although they look complex enough, I mean, how do they depend on S and T? Well, really quite straightforward. They're two linear equations in S and T. Remember, the vectors P, Q, V, and W, they're all fixed quantities. So all these squared magnitudes, all these inner products are just fixed quantities, some numbers that come from the initial setup of the two lines. What we're looking at here is a linear equation in S and T. Something times S plus something times T plus a constant equals 0. Similar structure in the second equation. So two linear equations and two variables can easily be solved, okay, using just direct substitution, or you can apply the algorithm of Gaussian elimination to that, okay, you know, for your linear algebra studies. Okay. So this is two linear equations. Two linear equations in S and T. So solvable using Gaussian elimination. Okay, so we can get out of that then a value for S and a value for T, and that will locate a value of S and value of T. That will locate these 2 points on the two lines that make the closest approach to order. Now that was one way of looking at it, one way of getting the solution out using a bit of calculus. We can also do it in a more linear algebra way, a more vector-oriented way. So if we return to the original setup, which was very briefly looked like this, two lines going by each other. Here says where the minimum distance is. Is there any kind of vector geometric or vector type considerations we can place on this sketch or this picture which is going to characterize when the distance is minimized? What kind of, how does this red line, how does this minimum distance line between L1 and L2, how does that relate to the lines L1 and L2 in a vector type way? Perpendicular to both, exactly. So we can use this principle that the minimum distance has to be achieved along a line which makes right angles with both L1 and L2. I.e., it has to be perpendicular to the vector V and the vector W. Okay, because v and w are the two direction vectors of the line. V is the direction of L1, W is the direction of L2. So what was this? Was R1 up here, wasn't it? And what did I call it? R1 and R2. Yes, this was R2. So yeah, that's good. Alternatively, so rather than going to the partial differentiation, alternatively we can say that the minimum distance vector R1 minus R2, remember that's something that depends on S and T. If you look at where we wrote our R1 minus R2 on the first page, it's a vector expression, but it's a two-parameter one. It relies on the parameters T and S. So it's got two unknown parameters into it. This minimum distance vector must be perpendicular, normal to perpendicular to both V and W. So that's another way to get the two equations out. Because in a vector type way, you can express this notion of being perpendicular by saying, well, so that means R1 minus R2, and you take the dot product with V, you must get 0. And when you take R1 minus R2, you take the inner product with W, that must also be 0. Shall we do it? So let's look at what those two equations are. So I'll go back to this expression. Remember this packaged expression for R1 minus R2 I had back here? Look just up your notes, you'll find this expression for R1 minus R2. This is my nicely packaged up R1 minus R2 is P minus Q plus T times V minus S times W. If I use that as the expression to put in for R1 minus R2 here, what do we get? The first equation becomes P minus Q, vector P minus Q dot V, and I've got a plus TV squared, TV dot V, and a minus S V dot W. That has to be 0. That's the first of these equations. And the second one, I get a P minus Q dot W plus a T V dot W. And I get a minus S W dot W. That has to be 0. And do those equations remind you of anything? Again, they are two linear equations in S and T, aren't they? This is just a constant here, this dot product, plus some constant times T, plus some constant times S equals 0. Similar thing for the second one. But if you just glance up your page of notes, they are exactly the same two equations as we got before from the partial differentiation. So if you have to divide across by 2, there's a fact from the partial differentiation, we pick up this factor of 2 in all of the terms. But if you divide across by that, on the right-hand side is 0, so it still have 0 on the right-hand side. Divide across by the 2 here. So see, these are exactly the same. So it's the same system as we have. Which is the same system as before. Which is nice. Yeah. Confirms what we've done before. But we can get to that. So rather than going to kind of calculus type ideas and using partial derivatives to locate the minimum, what that expression instead be used to kind of geometric ideas, vector type ideas, by saying that this minimum distance had to be achieved along this line from L1 to L2, which was perpendicular to both L1, both L1 and L2. So that's a nice run through with some vectors. Shows us using lots of vector operations and solving a geometric problem, finding the closest approach of these two lines. So let's give ourselves a little bit of an example to play with, or to solve. Just break up the proceedings a little bit. So, given L1 defined by the fixed point vector P, so I'll take P as being 1, 2, 0, and the associated velocity vector as being 1, 1, minus 1. And L2 I'll take to be given by the fixed point Q, which is 3, 1, minus 1. And the direction vector W I'll take to be 0, 1, minus a half. Okay, so find the closest approach of these two. Okay, so why don't you take a few minutes to work that out, and we'll have a look at the solution. If you've got any questions, feel free to ask, or questions about anything else, and feel free to work together and to sort it out together. Yes.
Is that V dot B or V dot W?
Up where?
Yeah, on that first equation.
That one.
Yeah.
But it depends. That's V dot V. So that came from taking, that's this first equation here, where I'm taking inner product with V. Yeah. Make sense? So you want to produce that system of two equations and the two unknowns from the data you have. You should have a system of equations. Those two equations in S and T. So you should just be a matter of solving those to find S and T. Signature sheet. once you have S, I mean, finding S and T is enough, I guess, because once you have that, you can then feed that back into your expression for R1 minus R2. You'll get a particular vector out, and you can just obtain the magnitude of that vector. Anybody got an S and T yet? Any other questions you might have, or any questions about the derivations we went through there? Shall we start working through the solution? All right. Has anybody got an S and T? Not yet.
What went wrong there? Ah, no comment here.
I did say last week, for anybody who wants to bring laptops along, they sometimes come in useful. And certainly for doing calculations like these, we can use MATLAB very efficiently. So we can quickly input the vectors. So PQ, 2 fixed points, and V and W, the 2 direction vectors, can input those into MATLAB. So then we can just set up the first of those equations. So the first equation was, now how do I undo this? Yeah, just do it out like this. So there was the dot product Or no, let me do it this way. See, I want to be talking about, I want to introduce the two variables s and t. So there's the command syms, S-Y-M-S, short for symbolics or symbolic variables, syms. So you can do syms s and t, and that will declare s and t to be two symbolic variables. And I can then set up my R1 and R2. So R1 of t is P plus T star V. I can set it up in this nice way, similar to how we described it. And R2 of S is going to be Q plus S times W. It actually evaluates the vector expressions that you've given it. So these are the vectors for the vector for R1 of T in the three components, and the vector for R2 of S. And then we can look at our two equations. So the first equation, so that we got out of using the vector geometric approach, saying that the line joining L1 and L2 had to be perpendicular to both of them. So that was saying that the dot product of R1 of T minus R2 of S, the dot product of that with the vector V had to be 0. So for setting up an equation, remember, you're representing an equation in MATLAB, or in most computer languages, use a double equal sign to indicate the equal sign in the equation. So remember, the single equal signs in computer programming stands for assigning this value on the right to this variable on the left. So EQ1 is that first equation. And it's a linear equation. Now it's for reasons of how the dot product is implemented, it's representing T and S as conjugate. Because in the more general picture of using vector scale or using complex scalars onto vector spaces, then the dot product, when you've got complex scalars around, they sometimes crop up as complex conjugates in that. But because the equations will have real solutions, the complex conjugate of a real number is just the same real number. So that's a kind of technicality that will just even out. So that's what the first equation looks like. So the coefficients you should have got there are 3 times t minus 3 over 2 times s minus 2, or maybe some scalar multiple of those. It might have simplified across by dividing out or something, I'm not quite sure. The second equation was similar to the first one. So this is equal to the dot product of R1 and R1T minus R2S with V had to be 0 also. So that gives us the two equations, so we can just solve them. You solve equation 1 and equation 2, and we can store the solution in a variable sol. So sol has two aspects to it, an s and a t, so we can look at the value of s and the value of t. Do sol.s and sol.t. For the solutions, the values of the parameters of these points of closest approach seem to be 3 for s and 13/6 for t. Okay, so you can get it to do the calculations nice and easily. And we can also just try and verify this by getting it to give us a 3D plot, which might help us to visualize this. So I want to actually plot out the two lines. So I'll set PTS1 to be the points. To get it to do the lines, I have to give it an endpoint and a start point. Now these values of s and t, they're both between 0 and 5. So I could choose, for R1, I could choose the first point to be R1 of 0, and the second point to be R1 of 5. So I'll draw the line L1 between t equals 0 and t equals 5. That will have the minimum value 13/6 somewhere in the middle of it. So those are 2 points for the first line, which I can then pass to a suitable plotting command. And do a similar thing for points to define line 2. And it's the same idea, but those will come from R2. R2 of 5. So PTS1 and PTS2 then are start point and end point of the two lines in 3 dimensions. So I can do a 3D plot of those. Now to pass the x and y coordinates through, you have to do some so this stands for the first column in PTS1, so those are the two x coordinates. And then you do similar construction, but now indicating the second column. So when you do the matrix brackets colon comma 2, this indicates the second column of the matrix. And that's the y coordinates, and then those are the z coordinates. So I've given it 2 x coordinates, 2 y coordinates, and 2 z coordinates, and it will draw the line between those two x, y, z points. So that puts a line in 3 dimensions. Okay, we'll return to that plot shortly. And you do hold on, so I want to add further things onto that same plot. I want to see the two lines in the same figure window. So I do the same plot command, but this time talking about PTS2. PTS2. So that will add the second line to the plot. Then I also want to get the 2 points which are closest to each other. So point 1, what's point 1? Point 1 is simply R1 of the value of t from the solution. Okay, because R1 of t gives you points in L1. So you can do P1 equals R1 of sol.t. And the point on R2, point on line 2, is given by R2 of sol.s. So those are the 2 points in the lines which should be the closest points to one another. So I'll add those to the plot as well. Let's go plot 3. I can do P1. Oh, I did P1 and PT2. Okay. P11, P12, P13. And I'll stick a marker. So when you put that asterisk in quotes, it's going to denote the point rather than just a single pixel. It'll stick a marker there. So I'm going to do the same thing for the second point, so I call that PT2. PT2. So this is to show you how we can use MATLAB nicely to join these two. And then I'll do the joining line between them. So the coordinates for the line, well, it's going from P1 to point 2. So it's the 2 points that's defined up there. P1 is the first row, PT2 is the second row. So I have my x coordinates, my y coordinates, and my z coordinates to draw a line between. So finally, that's the last thing I'll add to the plot. So I'll go plot 3, line 1, line 2, line 3, and make it stand out, give it a color. I think the other stuff will be blue, or it might have, I think it might start. I think this version might change the color every time you add something new. Anyway, so this will be a line from this point to this point. So this should be the shortest distance line on the thing. So finally, we can do hold off to close the figure and to get the figure to come up. It should just be behind this. There it is. And you can, with these 3D plots, so those are the 2 points. Now, why isn't the line joining them? Why didn't that come up? I seem a bit confused about that. I mightn't have done the last plot 3 command correctly. Why didn't I do? Oh, I didn't. Yeah, I should have. I didn't do the columns again about it. But you can see there anyway. So the the joining line didn't work. I think it just did a single point for that. I'll fix that in the version I upload. But, you know, as you spin that around, you can see that, you know, what we calculated, when we got MATLAB to calculate it for us, you know, it looks right. It mightn't look exactly the shortest here because of the way it does the projection to 2 dimensions, but it's, I mean, it pretty much looks as if it's right. Okay, so those 2 points seem to be the 2 points and the 2 lines that are closest to one another. Okay. So that's just to, you know, to emphasize that MATLAB is a excellent source to help confirm your work. Yes, yeah, I should have had this. I didn't do that correctly. I should have had the colon, comma 1, colon, comma 2, colon, comma 3. I'll fix that in the version I upload for you. Okay, is that okay? Any questions about that, or? Okay. So in this kind of thing, and in these assignments, you know, make as much use of MATLAB as you can, and use it to, you know, there's kind of no excuse for making calculation errors, you know, arithmetic errors. Because if at all possible, avoid doing arithmetic, really. So that's what I did there. You know, I got it to do all the dot products for me, and you know, you can set up these equations nicely. Where was it? You know, you can set up the equations in MATLAB, equation 1, equation 2, and just ask it to solve them, and it will. Okay. Okay, so before we end the session, let's look at one more example. Where's my notes gone? Here we are. Not that one that's written there, but I'll add another one on. So we'll go over to the screen there. So I'll add on a third one, and that's to, in 3D again, so in R3, find the minimum distance. These are typical kind of problems that might have to be solved in a virtual environment. Find the minimum distance from a point to a plane. Minimum distance from a point to a plane. So again, this kind of thing begins with a sketch. There's a plane in 3 dimensions, and we've got some point capital A. We've got a plane P. And one way we talked about planes was we said planes can be specified by giving a normal vector. You can have a normal vector to the plane, such as making right angles with the plane. And then of course, there's a whole family of parallel planes which have that normal vector. So to pick out one, you may need to talk about, you need to have a fixed reference point. So what's the minimum distance from this point to this plane? Well, we can sketch it in here. Let's call this point A prime. The origin will be down here somewhere. So there's this point A prime, which is lying on the plane P, and which is the closest you can get to the point capital A, while still remaining on the plane P. So the point A prime on P is the closest one to A. So we want to find this distance. And again, we use that same principle that we had to solve the previous problem. This minimum distance has to be achieved along a line which goes at right angles to the plane. So this itself makes this line itself makes right angles with the plane, any vector that lies in the plane. Okay. If it wasn't making right angles, then there'd be another point in the plane which was making right angles from A, and you'd have a little rectangle there. And so Pythagoras' theorem tells us that the hypotenuse of that right angle triangle is longer than this, well, its square distance is equal to the sum of the square distances on the other two sides. So the hypotenuse is the longer of the three sides. So the vertical side would be shorter. So this minimum distance has to be along a point along the line making right angles with the plane. So if we let little a be the position vector of the point A, and little a prime be the position vector of the point A prime. This notation is the vector pointing from the origin to A, the vector pointing from the origin to A prime, and so on. So this vector joining A and A prime is going to be little a minus little a prime. So since the minimum distance is achieved along a line perpendicular to the plane, normal to the plane, we must have that A minus A prime. Difference with these two vectors. So this is the vector pointing from A prime to A, or doesn't matter in which direction you take it. It's going to have the same magnitude. This must be perpendicular to the plane, or another way of saying that is this must equal lambda times the normal vector n to the plane. It must be in the same direction as the normal vector n. For some lambda, some scalar lambda. And lambda will be positive or negative depending on whether the normal is pointing to the same side where the point A is, or pointing away from it. And it depends whether you use this A minus A prime or A prime minus A. But that's where the meaning of lambda being positive or negative. So we want to find lambda. We find lambda. You see, n is known to us. N is part of the specification of the plane. So in any setup of a problem like this, where n would be known, okay, and the point A would be given. We're looking for this minimum distance. So the thing we don't know, or the thing we're trying to obtain, is the point A prime. But if we can obtain lambda, we know n, we know little a, then we'll know A prime. Okay. So in order to find A prime, we need to find lambda. So how do we find lambda? It seems a little bit off-putting, this situation, when we look at it first, because we got these two unknowns. A prime isn't known to us. Remember, n and A will be known to us. That's part of the setup. N comes from the specification of the plane. A is the specification of the point of the plane. So we don't know A prime, but we also don't know lambda. We've only got one equation. Although it's a vector equation, so there is 3 components to it, but then there's also 3 unknown components to A prime. So do we have enough? We've only got a single equation with those 2 unknowns. Do we have enough to solve this? Well, A prime and lambda, of course, are inextricably linked. Once you know lambda, you automatically know A prime. So really, there's only one unknown here. So on reflection, it should be enough. We just have this one unknown scalar quantity. We've got one equation for it, so that we should just be able to get the solution out. So how do we get lambda? How do we get lambda from that? Naively, what would you be tempted to say? I mean, if you gave that to a school child and told them you were trying to obtain lambda, what would they say? How do you get, if you got an equation, this equals something times lambda, how do you isolate the lambda on its own? I'm kind of inviting you to say something wrong. But you don't want to do that, so I'll say it. What you might say naively is, well, you divide both sides by n, because that will leave lambda on its own. And of course, can you divide both sides by n? No, because it doesn't mean anything. N is a vector, exactly. So you can't divide both sides. But nevertheless, we do want to get rid of it. So n is a vector, but if it were a scalar, we could divide both sides. So is there some way that we can neatly turn that n into a scalar? Sorry?
N dash. There's no n dash in the picture. No.
So n is a vector at the moment. Could you do something to it to turn it into a scalar?
I was thinking maybe divide it by
Multiply
cross it with
one of the vector.
maybe dot it or dot it with a vector that's perpendicular to it.
Yeah, okay, if you dot it with a vector that's perpendicular to it, although then that would give you a 0, and then the lambda would disappear. Cross it with one, but if you cross it with one, you get another vector. So this is very good on the right lines, but anybody pin it down? And n is known to us, remember. Well, one way to do it is instead of having the vector n, it'd be nice to have its magnitude n. Because if we just had the magnitude of n on the right-hand side, then we could divide both sides by the magnitude, because the magnitude is just a scalar. And what's a very neat way, given what you said, dot it or cross it with something, how do you obtain the magnitude of n, or something closely related on the right-hand side? You dot it with... So somebody could come up with it before I finish the sentence. Take the scalar product of both sides with... It's not something new, it's already there in front of us. Been repeatedly saying its name. N, yeah. Take the scalar product of both sides with n, because something magical happens then. Well, let's just do it and see what happens. Okay, so you take the scalar product of both sides with n. Oh. Okay, that's fine. Expand out this left-hand side. You can write that as, you can leave that as n dot n, or you can write it as the norm of n squared. Does that allow us to solve lambda? Well, you look at the things you know. Which things do you know? Okay, we know n, so certainly we know its magnitude, and we can divide both sides by it. Do we know this? Well, we know n. Do we know a? Yeah, we do know a. That's the position vector at the point capital A off the plane. So that's part of the setup of the problem. So you will know that. So we know this, just a scalar number we can calculate from the data. We know the norm squared there. It's a scalar we can calculate from the data. We know n, but we don't know a prime. Darn it, we don't know a prime, n prime. Or do we? Well, we don't have to know n prime, we have to know n dot a prime. What is a prime? If you look back to the sketch, a prime is a point on the plane. Now the plane comes with another piece of specification, another fixed reference point. What is n dot a prime? It's equal to something we know. It's equal to n dot q. So remember, the way the vector equation for a plane works is that every position vector, the position vector of any point in the plane, when you take its dot product with n, you always get the same answer. You get this fixed constant. I wrote it before, n dot r equals s, or equals p it was in the previous thing. It's a fixed constant for this plane. Okay? That constant, it's fixed by the specification of the reference point. So this is known to us as well. So i.e. lambda will be equal to 1 over the norm of n squared times n dot a, that will be known to us, minus n dot q. So everything on the right-hand side is, everything here is known data from the setup. Okay, so you can just calculate that sign, and then you know lambda. Lambda, remember, look at the top of the screen, lambda was the multiple of n, which gave you a minus a prime. So, i.e., you can turn this equation around and then say a prime is equal to a minus lambda n. A. So that tells you what the vector a prime is. You know a, you know n, and from this we know lambda. So you know what the vector a prime is. So you can certainly work out the magnitude of a minus a prime. So you can work out that in distance. Okay. But what we're seeing here is the mathematical argument using vectors and their properties and the properties of the operations that take you from the setup of the problem, specification of the problem, which came as n, q, and this particular point A, and lead you to obtaining the values of the necessary parameters you have to find the minimum distance. Okay, good. So that is, I think, the end of our consideration of chapter 2. So after the break, we shall begin chapter 3.